In 2018, the Turing Award, the Nobel Prize of Computer Science, went to 3 people: Geoff Hinton, Yoshua Bengio, Yann LeCun. Not for building GPT, not for AlexNet, not for any specific product, for keeping neural networks alive through 20 years when nobody wanted them, through the second AI winter, through mockery at conferences, 3 stubborn researchers who quietly kept the candle lit. Last video, we saw the 90-second neural network. Matrix, squish, matrix, squish, simple shape. This video, the human story behind why that simple shape almost died 3 separate times, and why the reason it survived is basically 3 people who refused to quit. Von gave us the mechanics: stack, matmul, squish, backprop. In theory, this shape can learn anything. In practice, for most of the 1990s and 2000s, that wasn't a widely believed statement. The people who believed it were viewed as fringe, which is where our 3 main characters come in. Today's puzzle: if neural networks were mathematically capable all along, why did they take 30+ years to work? And the answer is a mix of 3 things: not enough data, not enough compute, and a handful of specific engineering tricks that nobody had figured out yet. Our 3 godfathers each contributed to closing one of those gaps. Today's 3 beats. First, Geoff Hinton. Backpropagation, dropout, and the pre-training insight that broke the AI winter open. The one who was mocked the most. Second, Yoshua Bengio. NPLM 2003. The first neural network to learn word embeddings. He set up the whole L5 story 10 years early. Third, Yann LeCun. Convolutional networks. The first architecture that actually beat classical methods, and the one AT&T used to read your bank checks in the 90s. Beat 1. Geoff Hinton. In 1986, Hinton co-wrote the paper we mentioned last video, Rumelhart, Hinton, Williams, that showed backpropagation could train multi-layer networks. Huge result on paper. In practice, the networks people could actually train were tiny, and they overfit badly, so the field moved on. Support vector machines, kernel methods, Bayesian this and that, anything but neural nets. But Hinton kept going. Through the 1990s and 2000s, small lab in Toronto, grad students, he added dropout, a training trick that randomly zeroes out half the network on each pass, which prevents overfitting. He added layer-by-layer pre-training, ideas that nobody wanted, papers rejected, grants denied. Everyone told him to move on. And in 2012, one of his students, Krizhevsky, used a GPU to train a big convolutional net on ImageNet, crushed the previous record. That was AlexNet. That was the shot heard round the world. Krizhevsky's paper, with Hinton and Sutskever as co-authors, is the reason 2012 is the year everyone points to as when deep learning happened. And notice, the ideas were all Hinton's. He'd been publishing versions of them since 1986. The world just didn't have enough compute or enough data to prove they worked until 2012. Beat 2. Yoshua Bengio. Working out of Montreal. In 2003, he published a Neural Probabilistic Language Model. We touched on this in Lecture 5. Bengio was asking, if a neural network can learn any function, can it learn to predict the next word in a sentence? Turns out yes, and a beautiful side effect happened. In order to predict the next word, the network had to learn dense vector representations for each word. That paper is the direct ancestor of Word12ec. And of every embedding-based system afterward. It was too slow to be practical in 2003. Nobody paid attention. 10 years later, Mikolov made it fast. Everyone paid attention. That's an unusually clean case, often years too early. Bengio saw it. Bengio said it. Bengio published it. And the field went, huh, interesting, and moved on for a decade. Bengio's other big contribution, attention mechanisms. Bahdanau, Cho, and Bengio 2014. First serious use of attention in machine translation, which then evolved into the transformer paper we'll cover in video 5. The through line here, Bengio is the guy who kept saying let the network learn representations from the raw data at a time when everyone else was hand engineering features. Beat 3. Yann LeCun. New York. Convolutional networks. LeCun's whole insight. You don't need to connect every neuron in one layer to every neuron in the next. For image data, you can slide a small filter across the image. Same filter everywhere. Massive weight sharing. Way fewer parameters. And it works because the same edge is an edge whether it's in the top left corner or the bottom right corner. LeCun built LeNet 5 in 1998. Real system. Trained on handwritten digits. AT&T. Deployed it to read handwritten postal codes and bank checks. This was a neural network doing production work in 1998, reading actual mail, actual checks, while the rest of the field was busy declaring neural networks dead. The payoff moment for all three. 2012. AlexNet. Krizhevsky and Sutskever, Hinton students, using LeCun-style convolutional networks trained with backprop on a GPU on ImageNet, halve the error rate. That single paper won the entire field over. 6 years later, the Turing Award, not for any single result, for being the three people who kept the idea alive long enough for the compute and data to catch up. 3 takeaways before the quiz. 1. The 3 godfathers are Hinton, Bengio, LeCun. All 3 shared the 2018 Turing Award, not for a specific product, for keeping neural networks alive through the AI winter. 2. Each godfather closed a specific gap. Hinton, backprop, dropout, the pretraining trick. Bengio, neural language models and attention. LeCun, convolutional networks and shared weights. 3. 2012. AlexNet fused all 3 ideas: GPU, ImageNet, convolutions, backprop, halved image classification error. That single result flipped the field overnight. Quiz 1. What year and result marked when deep learning happened? A 1986 Rumelhart-Hinton-Williams published backprop. B. 2012. AlexNet cuts ImageNet. Error nearly in half using a GPU-trained convnet. C. 2017. Attention is all you need. Or D. 2018 Turing Award to Hinton, Bengio, LeCun. B. AlexNet is universally the moment people point to. The other events are all part of the story, but AlexNet is when the field flipped. Krizhevsky, Sutskever, and Hinton. GPU convolutional, backprop, everything fused. Quiz 2. What was Bengio 2003 NPLM about? A. A neural network that beat chess grandmasters. B. The first neural network trained to predict the next word, which produced dense word vectors as a side effect. C. Convolutional networks for image recognition. Or D. The Turing Award ceremony speech. B. This is the direct ancestor of Word2Vec and every embedding-based system afterward. 10 years before Mikolov made it fast, Bengio had the whole idea. The field just didn't have the compute to run it at useful scale. Quiz 3. What was LeCun's key idea with convolutional networks? A use more layers than anyone else. B. Slide a small shared filter across the image. Massive weight sharing. Way fewer parameters. C. Replace backprop with a simpler algorithm. Or D. Only use GPUs, never CPUs. B. Same filter everywhere. An edge is an edge, no matter where it lives in the image. LeNet 5 in 1998 was reading handwritten postal codes for AT&T, while the rest of the field had moved on to SVMs. That architecture is still the shape of every image model today. Back to the puzzle. Why did neural networks take 30 years to work? Because ideas need data and compute to prove themselves. 3 researchers kept publishing the ideas anyway. When the data and compute finally arrived, the ideas were ready. Next video, the specific architecture that made networks read text, RNNs. Next time, RNNs, recurrent neural networks. The first architecture designed to read text one word at a time, remembering what came before. Almost worked. Fell short of language in a very specific way. Hit subscribe.